Okay, everyone, welcome back to the class. Let me first share my screen. Okay, and let me have this one. Okay, so let me see. In the last class, we mentioned about support vector machine, and as a concept is very, very important. Let me first of all review the thing, review the theory part. So the basic idea of support vector machine is that we want to have, we have two. First of all, let's consider two classes. We have two classes, and we want to have separating hyperplanes to separate them. But how to choose a separating hyperplane? So to this point, we first define two margins, margin one, margin two, and then separating hyperplane without a loss of generality would be always in the middle. And then we just want to maximize the distance r, or actually you can say 2r, it doesn't matter. And then suppose the separating hyperplane, the equation is wtx plus b equal to 0. And as we explained in the last lecture, that no matter how you change, I can always write margin 1 and margin 2 to be wtx plus b equal to plus and minus 1. And hence I have these two lines, and then I can actually use the equation, actually the identity that x equals to x projection plus r times this unit norm direction. And then, do some simple algebra, and then you will get this. R equal to 1 over W norm. The meaning is that once I have the norm, then I can express the R. And then, as we mentioned, we want to maximize this thing. However, this one is in the new denominator. It's not easy in terms of optimization. So we equivalently try to get the minimum of the inverse, which is here. And again, this half is kept on purpose because, when we make the derivative, this half and a 2 going to be canceled. That's why. And then we write constraints in this way, meaning that suppose y equal to 1, which means it's in class 2, then it will be in this side. Indeed, if you substitute y equal to 1, you will have wtx plus b is greater than or equal to 1, which is indeed this direction. And then if y is equal to -1, meaning that it's going to go this direction. And indeed, you just plug in, you will see you can make my life easier. wtxi plus b is less than or equal to -1. So this is wtx plus b equal to -1. Less than -1, that means what? That means it's in this direction, right? And hence, yes, this model satisfied our requirements. And this is called hard margin SVM, support vector machine. So for target for new data, we will calculate, since we solve this model. By the way, one thing I do want to mention that this is for each training data, you have this constraint. Okay, so if you have n training data, you will have n constraints. Okay, now suppose we have already solved this model. We have the W star and the B star, which are the optimal solutions, to it. For new given data, what shall we do? Simple. We just plug in this x, and then we will see fx. And then we just need to determine whether this fx is greater than 0 or less than 0. Greater than 0, this direction, that means class 2. Less than 0, this direction, class 1. That's it. Okay, and as we just mentioned, it's called a hard margin SVM. But what does it mean by hard? Hard means these two margins are like a wall, meaning that I do not allow any points, let's say, get inside the margin or even across the margin. Unfortunately, in the real life, this is impossible. This is a wonderful, ideal theoretical model, but not a practical. In a practical, example, data are more likely to be like this way. So no matter how you define your separating hyperplane or your margins, there will be misclassified data. And then, unfortunately, this model does not work. However, we just need to revise a little bit. We can make it work. So the idea point is this: instead of brutally enforce this one to be greater than or equal to 1, we can involve, I guess I could put it here, we can involve a cassette and write the right-hand side for each constraint to be like this way. And also, in order to push Kasi, try to push Kasi to be 0, I'm gonna add this item in the objective function in which Kasi i's are all greater than or equal to 0. And this C is actually a regularization hyperparameter. The name is called cost parameter. So this C is also positive, non-negative, let's say. And then by doing this, what I have is suppose a data I is indeed very well, perfectly, let's say, stands in the correct side of the margin. Be careful. What I'm saying is in the correct side of the margin, not separating hyperplane, okay, of the margin. Then, as we mentioned, this constraint will be satisfied. In other words, Casi equal to 0, Casi I equal to 0 is satisfied. And hence, because my objective function is a minimization problem, and I do have a Casi I parameter, so of course the model will set Casi I to be 0. Because if Casi I is not 0, let's say 0.1, then my model objective function will be bigger, right? Since Casi I can be 0, 0 is attainable, of course, because I want to minimize. So of course, Casi I will be 0. Okay. Case number 2 is that Casi I is in the wrong side of the margin, but in the correct side of the separating hyperplane. For example, this x2. So wrong side of the margin means, correct side of margin, x2 should be somewhere here, but x2 is here. But it's still in the correct side of separating hyperplane. In other words, according to the rule that we just mentioned, if we plug in this x2, it will still be, less than 0. In other words, this data will still be classified as class 1. So in this case, we will no longer have, have this one, satisfied. Why? Because this is in the wrong side, right? However, if we have this case, think about it. This line is WTX plus B equal to 0. This line is WT plus B equal to -1. What's gonna happen here is that your WTX plus B must be between 0 and 1, right? And hence you will have this 1 minus Casi I between 0 and 1. And hence you get Casi is less than 0, greater than 0, less than 1. Here we go. So this is the second case. Case number 3 is, let's say x3, which is completely in the wrong side of separating hyperplane. And of course, if it's already in the wrong side of the separating hyperplane, then it is of course in the wrong side of the margin. So in this case, what's going to happen is this is equal to 0. And you should be here, but the truth is that you are here. And our equation side is greater than or equal to. So what should we have? We must have 1 minus Casi, which is what? Is less than 0. In other words, you are greater than or equal to a less than 0 number. And hence, you are feasible to be here. Because otherwise, if you're here, then no way. Sorry. Otherwise, if you are like, if this number is not less than 0, suppose this is 1, then you should be here. You know what I mean? So the truth is that this point is here. So in order to let a point to be here means crossing even the separating hyperplane, you must have this number is greater, is less than 0. In other words, WTXI plus B is greater than or equal to a negative number. So this is gonna be feasible. And hence I must have Casi greater than 1. So by doing this way, I can successfully define the soft margin SVM. Soft margin means, again, I allow data to be inside the margin or even across the separating hyperplane. And this model indeed is practical. And we discussed the two cases, which is if C is a big one, in other words, it has a big penalty, and hence, my SVM model will be relatively conservative, meaning that the margins tend to be relatively small. By comparison, if a C is a very, very small number, then my penalty gonna be very small. And hence my SVM can be more aggressive, meaning that I can tolerate more error. It doesn't matter because your penalty is very small. So why don't I just involve some error here and to make the first part, which is W norm to be smaller, right? So it's gonna be a relatively like big has a relatively big distance between the two margins. So these are two cases. Okay, so here are the SVM for two classes. And be careful when I'm saying here are the SVM, meaning that here are the linear SVM, okay? till now, we're all talking about linear CVM. Linear means the margin separating hyperplane, they are all linear functions. Okay, so what if we have more than two classes? So we discussed the two models, one against all and one against one. For one against all model, as the name, one against all. So for each K means the class. So suppose now I have M classes. For each K, one against all means I'm gonna choose this K to make the model against all. But basically the idea, actually, no matter one against all or one against one, the idea is that I'm gonna still consider it to be two classes, which is if it is in class K or it is not in class K. So this is the case for not in class K. And indeed, you can see, I mean, basically they're the same thing, because if this is -1, just time -1, it's going to be less than or equal to -1 plus Ci, right? So this is exactly here, the second equation. If it is in class K, we code the label to be 1, and hence it becomes this way. You just plug in y equal to 1. You know, that's actually super simple. Okay, be careful that as for each y equal to k, I have this model, and the total how many k's I have. My k can be class 1, class 2, blah, 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 until class m. Suppose I total have m classes, m is greater than 2. So I will have actually m such submodels. And then how can I make a decision? Easy. Again, okay, suppose, you know, for each model, for each submodel k, suppose my solution is C, the solution is wk star, bk star, and ck star. So I now give me a target x. I just plug in. I just plug in. So I will get an fk, right? The definition of fk is wk star t x plus bk star. Okay, so I get f1, f2 until fm, and then I'm gonna classify the data x to the class that has the biggest fk. So mathematically, it's gonna be returned like this way. I'm gonna have the argmax of this. So, and also as a special case when k equal to 2, m equal to 2, meaning we have two classes, this model is exactly the same as this model. Okay, and the case number 2 is the 1 against 1 model, meaning that I'm gonna, among the totally m models, I'm gonna always take 2 out. And the good point is that I only have like 2 groups of constraints. The bad point is that I have m choose 2, which is what m times m minus 1 over 2. Such submodels for choosing the pairs of k and l, because you're gonna always choose 2 pairs as the meaning 1 against 1. So you will have a lot of submodels, especially if your m, the number of classes, is a big number, then it's gonna be pretty troublesome. But the idea is this. So for the data, I only need to consider a small part of data, so that although I have many submodels, but for each constraint, I actually includes relatively small amount of the real constraints, which are only for the training data there that are in K, which means in K means in class K, I should say, which means the training data which are only in class K, and the training data they are only in class L. So I only need to take a small group of the training data to model each submodel, and then clearly we code the training data whose label is equal to k to be y equal to 1, and then the other one to be yi equal to -1. And again, I mean, we just substitute the things here. Again, exactly the same idea here. And then suppose I calculate, and we'll omit 1 against or 1 is here. Okay, now suppose I calculate the optimal solution for the KL, which are W star KL, B star KL, and C star KL. How to make a decision? We use a voting system, which is, so for the pair K and L, if this function defined in this way is less than 0, then I vote 1, class K gets 1 score, 1 point. If it's greater than 0, then class L gets 1 point. And then, totally, we're gonna run, m choose 2 such submodels, and then I will have a final score for each label. The label which has the highest score will win. Will win means I will, classify the target data X to be that label. So that's the meaning of SVM for two classes, one against one model. Okay, so so all the previous things that we mentioned are for SVM for linear SVMs. Again, linear means the margin separate the hyperplane are both linear. However, in real life, we could see some data like this way. So by a linear SVM, you will get something, like this. Well, honestly, it's not that bad, but if we can apply something like this, it will be better, isn't it? So we propose the idea of the nonlinear SVM, or professionally, it's called the kernel trick or the kernel SVM. Okay, so we need to see what does kernel mean. Here, this page includes a lot of mathematics. Basically, we use the Lagrange dual, and then since the function is a quadratic function, so we can use KKT conditions as both sufficient and necessary conditions. Again, if you're not interested, it doesn't matter. I mean, you can just skip it. I mean, directly see the examples. If you're interested, I have the things here, so you can read it. Although it takes it includes a lot of mathematics, but I believe after you understand much more clear to the kernel technique, how we kernel it, how can we make it a kernel, and the most important thing is why do we need the kernel? Why can we consider it in this way? Or why do I need to write the Lagrange dual? I mean, this model, let's say this model looks great. I mean, why? The key reason is the idea is, well, I do want to have the kernel. I do want the separating hyperplane and the margins to be curved. But how can I really, include this idea into my mathematical model? I mean, you cannot say I want the curve, then the curve. Machine doesn't know what I mean, right? You need to make a mathematical model. So in order to make a mathematical model, we need to see different forms of the problem. And since this problem here is quadratic, sorry, let me use soft margin. Okay, this one quadratic. So because this is linear, this is clearly quadratic, I can get a gradient. And also it's easy to see that this problem is actually a convex problem. And hence we can we can use KKT condition, and hence we can use Lagrange dual becomes both sufficient, and KKT conditions are both sufficient and necessary, and hence we can form the Lagrange dual like this way. And so you say why? Again, why do I need to have this way? Because this shows a great form that xi and the xj are in terms of the inner product. Then you immediately have the idea of the kernel. Why? Because why don't I change xi, xj to be a function? Instead of xi, xj, I write it to be hxi, hxj. Then isn't it immediately have the curve, right? I mean, here I assume your even if your h's are linear, I mean linear inner product from linear, it's not linear, it's still quadratic in terms of the form, right? So I immediately have what? I will immediately have this curve function idea. And also because again, I'm thinking I want to be even lazier. Why do I need to write the kernel as inner product of hxi and hxj? Since it only, you can see x only shows in this way, what I can do is that I can directly define the whole thing to be the kernel function, so that I don't, instead of this inner product of xi, xj, I directly have a k xi, xj. I even don't need to tell you which is the inner product of hxi, inner product of xj. I can save everything here to be directly replace this to be k. That's it. And be careful here, these xi, xj's are training data that are observed. They are not objective functions, okay? Be very careful. They are the things that we date. In other words, what I do is that I'm going to convert, a linear space, which is the x space, to be another space, to be a kx space, so that my coordinates can no longer be, like this kind of Descartes, coordinate. My coordinate is going to be something like I can whatever something like this way, it's gonna be like this way. It's gonna be, let's say this is k, let's say x1, x2. I cannot let me see how can I write it. I even cannot really write it in this way because the k is the value And this can be something like x1, x2. It's going to be something like this. It's difficult to plot it because at most we can only plot two. But the meaning is that I'm going to convert linear space to a nonlinear space. So this is the meaning. And then for the K, we typically have four types of the K. The RBF is the most famous one, and then linear kernel is easiest one. Polynomial, a bit more complicated. I cannot say better or worse. Better is in terms of the form. You can have many curves. Worse is, to be honest, it's not that practical. The more practical one is the Gaussian one. And the last one, sigmoid. If you do the neural network, you will always see every day you're gonna see this things, so that you're gonna hate it and love it the most. Okay, so this is the big story, the general summary story of the SVM series. Okay, now let's go to the part for coding. Okay, so let me see here. Let me go one. Lecture 10 SVM. Okay, so for this one, sorry about let me have a look at it first. What do we do is okay, at the better, first of all, have a look at this. Okay, so for this one, we will first of all generate the Gaussian distributions 2D, and then okay, minus plus 200. Okay, and then we will just print, use SVM to train it, and then we just plot the decision regions, use p-color mesh as we did before, and then we're gonna plot. This is probably use contour. Yes, use contour. We're gonna plot those margins separating hyperplane, and also we're gonna circle. I believe I use scatter, right? Make a bigger size and make the face color to be none, and hence it's not gonna be filled. It's kind of like cheating way to circle those points. So then we can make it. Okay, let's make it. But still, I need some cheating things to what to get the parameters. Okay, so import numpy as MP, import matplotlib.pyplot as plt, and then sorry about that, something fall down just okay, and then I'm gonna do what I'm gonna let's say I'm gonna from sklearn sklearn dot I forgot what is that sklearn dot SVM, sorry. SVM import SVC. Okay, so now I can first of all generate the data, generate the let's say Gaussian this distributed data for training data. And then I can have x1 equal to mp dot random dot multivariate. Come on. Okay, here we go. Gaussian. And then I need to open my cheating sheet. By 0. 92 to 36, 100. Y1 equal to mp dot once 100. Y2, x2, y2, x3, y3, and then here's gonna be 3 times. Here gonna be 2 times. Oh, well, I meant wait, what I'm doing here. I don't need a y2, y3. Sorry, that's like a habit. I always use 3 classes. And then the next part is the parameters -5, 0, 4, 2, 240, 120. 120. Okay, 2 times. Okay, here we go. So this is the training data, and then I need to concatenate mp dot concatenate x1, x2, x is equal to I'm gonna use it for rows, and then y equal to mp dot concatenate y1, y2, and also x is equal to 0. And then I need to do what? So later I will plot it. So I will have x1 equal to np dot link space x dot x 0. I mean, I remember just now I saw it as negative phi and a positive phi. 0 dot max plus phi 200, I remember. And then I just copy and paste, make it to be x2 equal to this, and then create a mesh. Because I need to make it a p-color mesh to plot the decision regions. np dot mesh grade x1, x2, and then wait 1 minute. So that means I forgot something here. From sklearn dot colors. It doesn't show me anyway. Then I'm gonna import. No. List. That means it's colors. Every time I cannot remember colors or colors. Import listed. Wait, let me have a look at. I didn't even import here, so how can I run it? Oh, here. No, that's killer. Sorry about this. There is something wrong. Matplotlib dot colors. That's what dot colors. Import listed. Color map. Okay, so now I need to have the color. I have decision region color equal to listed color map, and then it's gonna be our favorite color, which is a light coral, light green, light. Oh no, here I'll have two classes. I don't need a light blue anymore. So in this case, I already have the initial settings. So I created these things. Okay, now what we need to do is we need to have the SVM training and the subclass, right? So let's say SVM training and subclass. Okay, so first of all, I need to create a figure equal to plt dot figure. And then let me show the lines again. Where are my lines? Okay, and then I need to have what? I need to have, let me think about it. Then I need to have a subplot, and hence I need an I. So now I can have a, let's say, k list equal to what are my k's? 0.1, 1, and 5. Okay, so now I can have for let's say no, I can call it, let's say let me think about C list, not K list. C list for C in C list. I will have first of all, I need to train the SVM model equal to SVC. So for SVC, first of all, so let's see whether it has some cheating things here. No, it doesn't show me. But for SVC, first of all, it's gonna ask you what is the kernel. And the default kernel is actually the Gaussian kernel, the RBF kernel. And so here, I'd better put a linear, because here I want to use the linear SVM instead of kernel SVM. In the later examples, so we're gonna all see the kernel SVMs, so that we're gonna have kernel equal to linear. And then another thing is, remember the regularization or the cost parameter C here. I need to define the C. What is that C? And the C is already in here, so that we can say C equal to C. Okay, now I already have this model. I can just model the fit X and Y. So here we've already trained the model. Then the next thing is that I need to plot the data, right? So first of all, let me write some comments here. Train the linear SVM. And then let's say subplot the training data. And then we have x equal to fig dot add subplot let's say 1, 2, 3. So I'm gonna have, let's say 2 by 2, because totally I will have 4 figures. And then and then I have this. So I will have ax dot plot and so on. So I'm gonna, because I already know these two groups of data, I'm gonna plot x1 first, and then r dot, then label equal to, let's say, training data class 1. And then training data class 2. Okay, so here I plot the training data. And now I need to plot the decision region. Plot the decision region. Decision regions. Okay, so I have what? I've already have these settings, right? So I can directly plot the prediction equal to model dot predict. Okay, then we have the same thing here again. NP dot array dot transpose. Then inside gonna be x1 dot revel, x2 dot revel. Okay, so now I already have my let me see here. I already have my predictions, so I can use p color mesh x1 x2 dr predict. Again, come on, there we go. Dr predict the reshape x1 dot shape, and then have a cmap equal to dr color. Okay, here we go. So this is how we can actually make a thing. So now I can just plot it. Let's say, let me give it a title. Set title. Let's say what? Let's say SVM with, let's say SVM. Let me just make it a linear SVM. Here SVM at C equal to C. So that's a thing. Okay, now I can just, plot it x dot legend. Don't forget I plus. So PLT. So this is a very fundamental thing that we are gonna, again, wrong, great. And integers required, so where? I, uh, let me see here. Wait. What is wrong? I need to require multi. Oh yeah, no, not multinomial. Sorry. Not a nomial. Oh, that's the reason why. Multinormal. Okay, here we go. So let me just make it outside. Let me make it matplotlib pt. So it will get outside. Okay, here we go. So this is SVM, and C equal to 0.1, C equal to 1, and C equal to 5. Okay, so and then the next thing is that as we showed in the slides, we want to have those kind of decision, this kind, the margins separating hyperplanes, and also the circle, those kind of support vectors. Again, support vectors means the vectors inside, the points inside. Okay, so we can first of all plot support vectors. So why? Because it's easier. Okay, plot. Let's say let's say circle. Let me use the term circle. The support vectors. So basically, again, what you have is suppose these are support vectors, right? Basically, what you have is to use a scatter. So what do you need to do? Because for the model, it does have a parameter called support vectors. So if it's a support vectors, you just have a circle, and as we showed in the slides, the trick is that the four color is gonna be none, so that there's gonna no face color, not four color face. There are gonna be no face colors, but the edge color is gonna be something. Let's say I have the edge color black, I believe, or blue. Blue, okay. The face color is blue. So in this case, I can just make circle it. Basically, you're still, actually plot the points. X dot scatter. So what you're gonna plot? So what I'm gonna plot are the model support vectors. Model dot support. Yeah, here I need this one, otherwise I will make mistakes. 0, and then similar model support vectors column. Okay, now I have this one. What I'm gonna do is that first of all, I'm gonna make size equals to 100 maybe. Let me see. Yes, 100. Next time I'm gonna have a double screen, so that my life is gonna be much easier. Make my water light this way, and then I'm gonna have face color. I believe face color equals to none. And also I'm gonna have edge color equal to, as we just mentioned, blue. Okay, so in this case, I'm gonna have what? I'm gonna have the circles. Let's run it. Okay, here we go. So now we already have, circled all these. These are support vectors. What we need to do is the next step is to what? To have plot the support. Plot the separating hyperplane and the margins, right? The thing is that, well, think about this. It's uh you can definitely kind of like let me see. You can definitely use the mathematics here to brutally compute it, but it will cost a lot of like human calculation, I'll call it. And an easier way is that we can use the contour lines. So remember, for the contour lines, we have we have the shift. So here in the 2D contour lines, we have something called levels. So we can have different levels of the contour lines. But what is your basic level, right? I mean, for your basic level, you cannot avoid. Well, my basic level is this support hyperplane, separating hyperplane. So the separating hyperplane is actually what? Is actually WTX plus B. That's what we have, right? Well, this is 2D. So the WTX plus B means what? Means WTX plus B means W1x1 plus W2x2 plus B. So I already have W1, W2, and also the B. And hence, I just need to plot the hyperplane, separating hyperplane itself. And then I can use a contour to make a shift, which is the left shift -1, the right shift -2. Sorry, +1. So that I can make my life easier. Of course, you say I don't want it. I just want to brutally plot 3 lines. Can I? You can absolutely do it. I mean, I just want to be lazy, to be honest. So, okay. So to this end, what I want to have is I need to have, suppose I already have, things. I need to have a y, and then wait a minute. Let me give me 1 second. I have x1, x2. To make sure that I'm not gonna have notation error. Let me make it to be z. I'm gonna have a z, and then give me 1 second. Let me think about it. Okay. So first of all, you will need okay, here we go. So I will have this for I. No, I already use I, so I'm gonna use, let's say, AB for A in let's say range of x1 dot shape. So this means in the number of the row, how many axes I have, how many rows I have. Actually, row means column, not for B in range of x1 dot shape 1. Then I'm gonna have your ZA. Wait. If that case, I need to define the Z here as well. So I will have Z equal to, let's say, NP dot, let's say zeros. let me use empty empties to make my life easier. Empty PV, let's say x1 dot shape. So I've already defined x1 here. So I will have the shape or empty matrix that's gonna be okay. Now I should be okay. Now I have ZAB equal to W1 x1 plus W2 x2 plus B, right? Okay, so W1 x1 is a model dot coefficient dot COEF. Okay, so it's gonna be 0, 1 times x1 a let me yes, AB because x1 are arrays and this coefficient is actually a 2D. And then I can have a model dot coefficient of no, sorry, 0, 0 first, not 0, 1. Here 0, 1 times x2 AB. So in this case, I already get to the x and y's here. And then I'm gonna have what? I'm gonna have the model intercept, model dot intercept. Okay, so give me 1 second. So this is x1, w1 times x1, w2, x2 plus this one. Okay, now I have the z here. Then I can what? I can have the z, I can have the contour, right? Ax dot contour x1, x2 based on whom? Based on z. And then I'm gonna have a, let's say, levels. This is the key point. So I can make 3. So, in this case, I can be a lazy man. I can just write plot like this way. And then let me try it first. Let me see. Oh, here are the warning, so we can just ignore it. Okay, here we go. So ugly. So give me a color. So let me see here. So what I'm gonna have, let's say colors equal to B. And then let me see what I did here. Oh, I set up a line style must be. Yes, here we go. Line styles. And then line styles equal to dash. This is a solid line, and then dash again. Hope it's gonna be more beautiful. Okay, here we go. Great. Okay, so this is the thing that we have seen in the what in the slides. So here we go, and training accuracy. So simple. You just okay. Let me just add it. So you just add something super simple here, and then you're gonna have, let's say, training accuracy equal to here's just model dot score x y. Let's say, let me make a 2 digits. Okay, here we go. Now I think everything's the same. Yeah, everything the same as the slides. One thing is that again, because we randomly generate the models, randomly generate the data. So the training data, the plot is a bit different from the what. It doesn't make any difference because I should have 3 digits instead of 2 digits, but it doesn't matter. So the key point is what? The key point is I want to see the performance, between different those C's first. And indeed, you can see that when C is a bigger number, which is equal to 5, it's smaller. You see, it's a thinner. And when C is small number, the margin is fatter. Again, because C is small, will give me an aggressive SVM. Aggressive meaning that I can include more, I can tolerate more errors inside. When C is big, meaning a high penalty, meaning that I need to be more conservative. I cannot tolerate too many errors because the penalty is too big. So that's the thing. Okay. So let me see here. This is the initial example. Then we can actually use SVM in many more aggressive or more interesting data sets. So here is something called make moons. So the original data looks like this way. And if we see the data this way, the first reaction we're going to consider is what? The kernel. Because think about it, how can you use, a linear SVM? A linear SVM will probably be pretty bad. So here I have the, the comparisons here, and then let's see, how can we make it? So first of all, I still need to jump the data. So the data is already included in Python this data set is called make moons. So let me just copy and paste. I need one more thing, which is from sklearn data sets, import make moons. Make moons is here. Okay, so first of all, I'm gonna generate the data and plot the original data. Generate the training data, let's say. Okay, so we're gonna have xy equal to make moons. First of all, how many samples do you want to have? N samples equal to 1,000 probably. Wait, what happened here? Let me see. 1,000 noise equal to 0.2. Okay. So the noise equal to 0.2 means that okay, so define noise, these are noises, something like not perfect, something not that good. It's kind of like a noise level. Okay, and then I'm gonna have what? I'm gonna have the lists, right? Because here I just generated X and Y. I know I have two classes, but what are the labels of the two classes? So I can simply write like this way, class one list equal to, let's say, I for I in range of x dot shape 0. So this means how many points if y I equal to 1. Equal to 0, sorry. First of all, give me a second. I should have mentioned one thing before, which is to have a look at x and y. Let me have a look at x. So x are just those data, and for each, for it's a 2D data. In each row, it includes a coordinate, so where the point is. And I can print, for example, x dot shape, y dot shape. So x is 1,000 data, because we ask it to generate 1,000. 2 dimensions means the coordinate. Y is the label, also 1,000. Let's say I can just print y. It's gonna give you 0 or 1s. 0 means, the first class. 1 means the second class. Okay, so what does this mean? So of course you can write it, you can definitely write to write it to an I and say that, let's say class one list equal to empty. And then, okay, let me just write down. You can just write like this one. Class one equal to, let's say, empty. And then you can write, for example, for I in range, let's say x dot shape 0. So, okay, so if y I equal to 0, then what are you gonna do? If it equal to 0, then you're gonna class append, right? Class one dot append I. Otherwise, if it's not equal to 0, that means it must be equal to 1. Else, then you're gonna say class 2 list. So you're gonna define a class 2 list here. Class 2 list equal to empty. 2 list dot append I. So what's the point? The point is that I will have class list index set, class 2 index set. So I know which points belong to class 1, which points to class 2. You can definitely write in this way, or you can just write in this way. So which is a simpler version. So class 2 list for I here if y equal to 1. So this is just to be lazy, to be honest. So that's the point. Okay, so now I already have the index sets of class 1s and class 2s. So what can we do? We can just simply, based on the x and y, I can make it x, right? X1 means the points that in class 1 is going to be what? Going to be x class 1 list. Come on. Okay. And then x2 equal to x class 2 list. Come on. Okay. So that's a point for us to have these two. And again, these and these are equivalent. Okay. So now you can just simply see, for example, if I want to say y1 equal to let's say y class 1 list. And then here, of course, you don't have to write it. I just want to show you the example. Class 2 list. Okay, now if I print y1, you're gonna see it's everything 1. You see it? If I print y2, oh wait. What? Oh, sorry. Here's 0. Okay, yeah. Now it should be all 0. And then y2 should be class 2 list, means it should be all 1. So here we go. So that's the point. So that later, because we're going to do the plots, so that I can, plot the class 1, class 2, and then make the labels. Otherwise, I mean, you can plot everything, but how to show different colors and make the corresponding label? You know what I mean? It's going to be very difficult. And that's the reason why I just use these 2 lines, these are 4 lines, actually, 3 lines. This one is actually not needed, to separate, the classes. Okay, now since we've already separated the classes, what can we do? We can just plot, right? plt.figure, create a figure, and now we can have plt.plot x1, 0, r label equal to training data plus 1 plus 2 rg, and then I can just make, plt.legend, plt.show. Here we go. So let's say RB, let's say. Let's use blue color. Okay, here we go. So this is the thing. And by comparison, let's see what if my make noise to be 0.8. Okay, now let's plot the data again. Now I understand the point of noise. This is a who knows what is that, right? Okay, or I can make a noise to be, let's say, I don't know whether it allows 0 or not, but let me try it. So this is this is noise equal to 0, and you can see it's a perfect data, kind of like there's no noise at all, and you can of course make a noise to equal to 0.1. So the bigger noise value, the bigger noise is. So let's go back to the first one, noise 0.2, so that you can see indeed there is something. So the point is that I want the data to kind of like enforce the data to generate those kind of misclassifications. And I want to see how SVM performs. And later, I believe in the last example, we'll actually compare all compare all classifiers that we learned in this class so far. So this is the point. Okay, now we've already finished the initial setting. What shall we do the next step? We need to train the SVM, right? But here in this example, I want to show you the results of different kernels. And so we consider, I believe we consider three kernels. Let me see. Yeah, 3 kernels: RBF, polynomial, and a sigmoid. The reason we don't do linear as linear is just too simple, too common. And for a different kernel, I will have the different gamma list. So gamma is here. So the gamma is actually a parameter. And let me see here. Let me see here. I believe okay, here we go. So this is the gamma parameter here. And I believe we need to go to scikit-learn. But in the scikit-learn document, sklearn, let's say SVC, let's say gamma. Okay, let me see. There's a place I forgot where, but you can see the kernels, all the kernels and the definition of the kernels. So what scikit-learn library did was kernel. No, not kernel functions. Okay. So okay, here we go. So this is their definition of the gammas, and you can see the polynomial is defined in this way. So in my polynomial, there's no weight here. So the gamma in scikit-learn is the weight. For these two are exactly the same thing as these two. Okay. So that sklearn library, scikit-learn library does include a parameter called gamma. And in my slides here, I set up compare different gammas and versus different kernels. And then let's see how we can make it. So let me make it smaller. So now I can do the SVM training. Oh, that's great. train the SVM under different kernels and gammas. Okay, so first of all, I have figure equal to PLT dot figure. I actually love it. In this case, I'm no longer going to worry make any mistakes. I can just read for it. Okay, but anyway, so the case is this. The case is I set up for kernel and then I set up for different gammas. Okay, so I can say let's for kernel in RBF poly sigmoid. So these are kernels that secular includes so that you can read the documents here. Let me see kernel functions. Here we go. So you can do these things. And then I'm gonna set up the gammas, right? F kernel equal to RBF, gamma list equals to 0.1, 110, 100, else if kernel equal to let's say poly, gamma list equal to 2468, else gamma list equal to 0.01, 0.1, 110. Okay, so now I already have my gammas. Now after it, what should we do? We can actually train it. So I can just say for gamma in gamma list, we can train the model equal to SVC. Be careful, the things are here. So kernel equal to kernel. Here, one thing I want to say is this, the setting of the C. Remember in our first example, we do have C, right? So by default, C is equal to 1 minus number of features times the variance. So in our example, sorry, but by default, C equal to this and gamma equal to this. So the number of features here is 2D, so I have two features. X dot variance means the variance of the X. So this is default setting. But here we just use C to be the default, C equal to 1. We don't set up anything here. Kernel equal to kernel, and then gamma equal to gamma. Because this gamma is for gamma in gamma list. So here, and then I can have model dot fit X and Y. Okay, now I have already have these things. So what shall I do for the next thing is I need to plot the data, right? And here 1, 2, 3, 4. I have 4 gammas and I have 1, 2, 3, 3. So it's gonna be what? It's gonna be 3 rows and 4 columns. So I'm gonna have I need to define I. Oh, I defined already. That's a good point to open this one, copy and paste. Great. Okay, so now I have this one, and then I can let's say subplot the training results. So I can have let's say ax dot figure dot add 3 row 4 columns I, and then ax dot plot. The same thing here. I can just copy and paste. Let's say train data 1 R, and then train data 2, which is blue. Okay, and then I need to do the decision regions, right? And then I'm gonna have dr predict equals to let's say model dot predict, and then np dot array. Dot p. So this is gonna be, let me see, did I well met I haven't defined those things. So give me a second here where I looks like I forgot to define something here. I need to define something. I thought I already defined. 1 second. So I can just simply copy and paste things from here. Whereas the things here, okay, here we go. And then I need to do one more thing, which is, oh, I already have X. I don't need to concatenate anymore. X1, X2, X the maximum. Let me see here. 0.1, 0.1, 500. Okay. I believe 200 is enough. Okay, so I have all these. I have this. How many classes? I have 2 classes, right? And here I have model.predict. Give me 1 second. So I have the things here. And then did I define the okay, yes, I defined x1 dot level, x2 dot level. Okay, so now I have the decision. And then after that I can use what the p color mesh. I can have x dot p color mesh x2 and then predict dot mean shape one dot shape and the c map equal to dr dr color. Okay, so in this case, I've already wrote the prediction here. So now I can set up the title. Ix dot set title. Let's say SVN with kernel. Let me see here. Yeah, kernel at gamma equal to gamma. Okay, here we go. Whoa, what happened here? First of all, extremely important thing, I forgot I plus equal to 1. Second, do I have any other mistakes? Let me see here. Hope no. Okay, here we go. So I have uh oh whoa, I know wait, 1 minute. Here, let me see. First of all, the color is wrong. Light blue. Second, let me see here. Whoa. 3, 4, I. Why it is in this way? Let's see, gamma in gamma last. Wait, let me. Oh, that's really stupid. Okay, here we go. I know it doesn't look very beautiful, but let me just. Okay, and indeed you can see the training results for these kernels. You know, they're not that. Okay, I forgot the legend, but not a big deal. You know, everybody knows. You know, the legends. You know, one group of the training data, the other group of the training data. The thing is, where's my training accuracy? I believe my training accuracy here. Oh, okay. Let me see. How can I put a training? Okay, use ax.tax. Okay, so negative 0.1. Okay, so this ax.tax is something that I can write a text in the figure. So here is like the button horizontal part, which oh wait, sorry. This is the button horizontal part, which is negative 0.1, which to move it here. And this is the button vertical one, which is, you know, in other words, I want make the distance to this edge and to this edge both to be 0.1. And then what do you want to write, which is the size, the score and the size. Alignment, horizontal alignment is right. Let me just add it here. Where it is. I can, you know, add any place, it doesn't matter. So that I'm gonna have ax dot text. The first of all is what's the distance? Let's say 1 dot max 0.1. Here is the horizontal part, sorry, vertical part, +1. So that will be there. And I do need to have the horizontal alignment, I believe. How do you spell alignment? ALIGN alignment equal to right. Okay, so this is the thing. So I should be able to, oh, well, the most important thing I forgot, which is model, what do you want to print, which is model dot score X and Y. Okay, now let's see. I hope not too wrong. Okay, here we go. Great. So now we can, what's so ugly? That's interesting, huh? Let me see. Okay, that means my water too bad. Here we go. That's the reason why. Horizontal. Do I have something else? So I can actually, I don't actually need to have this one. 0.1. So this means the horizontal, sorry, the vertical, gonna be a bit more. And then because here my horizontal alignment is 0. So I define it. In other words, I define it at this corner, Okay, so here we go. And are you kidding me? That mean, let me see what did I write here? Oh, it should be x2 because if you use x1, then it's gonna be cross. So that's gonna be the other side. So it's not this one. Sorry about it. Okay, okay. Okay, here we go. Hope this, yeah, this time everything's good. So this is the kernel, RBF kernel. Whoa. Oh, sorry. Row. Each row is the yes, the row, not column. Sorry. So for each row is the one kernel. So this is the RBF kernel, RBF, and this is the polynomial, and the last one is sigmoid. So these are different gamma settings, and you know what? Indeed, you can see for the RBF kernel, it's actually pretty strong. And that's also, if you compare these data, you can see almost every group, except for the first group, almost every group, the what? The RBF kernel wins. You see the prediction? And from the picture, the decision region, we clearly see it. Be careful of one thing that, for example, like this one, it's clearly gamma is too big. You know what I mean? Because this looks like an overfitting. You need to be very careful because what if, let's say, some points are around here, it will be kind of like classified to be the red class, which is clearly wrong. So in general, what we like is something like this. And indeed, in many cases, the setting gamma, which is 1 over number of features times variance, this is actually a very good setting. And indeed, you can actually use something like that in, in application. So that's one thing for SVM compared with different kernels. And you can clearly see the power of this this nonlinear kernel compare versus those kind of linear kernels. Linear kernels, for those kind of the linear kernel performance will be super bad. Will be something like that. And you can see, I'm surprised the training accuracy is still high, actually, because only these and these parts are wrong, all other parts are correct. But compared with the results, for different kernel with different gamma settings like these things, this result clearly is very bad. So this is the thing of the kernel functions. Okay, for the next example, let me see what's the next example. As the next example is the that's my favorite. The next example is a SVM in hand return digits recognition. First of all, nowadays the hand return digits recognition has been very powerful. So basically what it is say I write a number, so human can read this too, and I want the computer to read it. Hey, what is this number? And so for example, I write a letter, whatever thing, right? And it wants the computer to automatically recognize, convert, a picture to be the text. So this is the fundamental idea of of handwriting recognition. But here, to make my life easier, we'll only discuss the case for hand return digits. Another thing is that nowadays people all use neural networks, but the truth is that you do not have to really use neural networks. You can actually use SVM for the number of dimensions small. Okay, so here in the training data, scikit-learn itself has training data for the digits called the load digits. This training data for each picture, it includes only 8 by 8, which is 64 64 pixels. And for this small number of the training data, SVM works actually pretty well. And it's actually the training procedure is actually very fast compared with neural networks. Of course, in general, neural networks is a way better because it can include so many layers and make the prediction accuracy to be very, very high. I mean, really, really high. And then even if, let's say, you include many, many pixels instead of only 64 pixels for one digit, it can really well recognized. The level is even better than myself. I mean, they're like human, at least for me, than human like a recognition. I don't think we will have the time to mention the neural networks in this class, but here let's see the results of the SVM. You may be surprised because such a super simple SVM can get so good results. So let's first start the thing. I actually even don't need this one, I believe. Okay, but I need to load from sklearn data sets, import load digits. Okay, so first of all, I'm gonna, let's say, load the training, let's say, digits data. So I'm gonna have digits equal to load digits, and x equal to okay, first of all, you can have a look at digits. Let's say print digits. And you can see indeed I have the data part and then I have the target part. Okay, so here I'm gonna say x equal to digits dot data and y gonna equal to digits dot target. So let's print x first, then print y. And you can see indeed x is just the data of the pictures are actually writing this way. X dot shape. Y dot shape. Okay, so X dot shape is this, and you can see it includes 1797 rows, and each one is 64. The 64 data means what? Means vectorized image. So it is actually 8 by 8. And the Y is nothing but the what? The data. The label. So it's gonna be 1 to 9, right? Meaning that this image is actually the class is 1. This image, the class is 2. That image, the class is, let's say, 9. That's the point. So the first thing is that, it's not a tensor. If it's a tensor, you can simply just, plot it, but it's not tensor. So our very first thing is that I need to kind of like reshape it to be what? To be the 8 by 8 image, and then I can plot it. However, there's another thing. You know what? The thing is, because I believe I set up the margin to be 12. Yes, here we go, 12. You can definitely making that one that simply just use, now 64. You just make it, let's say, you make it to be reshape. So it's gonna be looks like, oh, it's so easy, right? I just reshape it to be 8 by 8. Great. Use the reshape method. The point is, if you use that method, let me have a look at this. So sorry, all of your data here, they're gonna be no space. So you can see there's some space here. The space is actually 4 because I make it to be 12 instead of 8. If you just reshape it, they will be super tight. Not to mention here the same. It's gonna be like everything just all together. It's in my personal view, it's gonna be something like this. You know what I mean? It will be like this way. altogether. In my personal view, it's not easy for human reading. For computer, it doesn't matter. And hence, I recode everything instead of simply just use the reshape. And in my code, I manually code the locations and I set up the distance to be let me see, to be 12. Yes. So here what I have is, give me 1 second. So here what I have that for each row in the image, I'm gonna print 40 digits, and then what I mean is this. So 1, 2, 3. If you just count it, it's gonna be 40 digits in each row, and then the distance of that I coded to be 12. 12 times the rows plus 1. So that's the thing. So in this way, I think I can make it kind of like relatively, sparse, easy for human to read it. So that's the point. Okay, now let's just do it. Okay, so I have axis and fy's, and then I can say let's say plot the images of the training digits. Okay, now how to plot? So first of all, I'm gonna have, let's say, number of image per row equal to 40 as we mentioned. And then first of all, what I'm gonna do is that because I really need to convert everything to be an image. So I need an image matrix. But since I don't know what is that now, so I temporarily just make it to be 0. Another reason I make it to be 0 is that 0 means empty. So that for the margins, they should be 0. So I make it 0. I only need to change this for each digit 8 by 8. Then that's it. So I'm gonna say image equal to mp.zeros. And how about the dimensions? So again, I'm gonna have 12. For each I will have a 12 by 12 instead of 8 by 8 for each digit image, so that I should have how many rows? I should have 12 times 40 nums, and then the height is gonna also be 12 times 40 num of image per row. Okay, that is excuse me. That is the thing. So for my image, so originally I make it to be 0, and now what I'm gonna do is I will generate this image. So I'm gonna say for row in number this one, and also I want to make let's give me 1 second. Okay, so this defines the rows. Then I need to I better plot something, otherwise it's gonna be. So remember my axis for each column, for each row, sorry, it's like this way. It has 64. Sorry for the plot. It should have 64, right? Okay, so now I have give me 1 second, let me see number. Now I have this number of the wait, sorry, first of all, one thing, stupid thing, range, not the. Now I have this number of the for row in range number of the rows. Yes, for each row I need to find the start of my picture X, because so the picture X is if I'm in this row, I should have what? I should have 12 times the row, yes. X, let me say, let's call it X start equal to okay, this plus 1 means just index, because you start from 0. And then so for each, if one row is kind of let me see, if one row is gone here, but each row includes 12 pixels, so I'm gonna have this one, and then let me see, then I'm gonna have a column for column in range of non-image per row, and then I'm gonna have, let's see, but how to get my columns? my column is gonna have and then no, it should be the same because both of them are 12 by 12. Yes, equal 12 row plus 1 as well. So now I'm gonna have, wait. It should be times column, sorry, not a row. Times the column. And then once I have the X start and Y start, what I can do is that I can really write to the image because I want to convert those things to a image like this way, to an image like this one, so that I need to determine the image start in the, the start point of this. So when I say image start point, what I mean is this one. So I have so many, let me just plot. I have so many of those. To save my life, I just plot, this. Each of them is 12 by 12. So then I want to have is for each image, I want to see this corner. What should your coordinate be, right? Because I've already known the rows. Each row has 12. So the start of here should be X is 12 times the row plus 1. The Y is similarly 12 times column plus 1. Once I know the row and the column numbers, because they are in the range of this one. And then what I'm gonna have is I can have the image now. I can have, so the image, since I already have X start, and also I know for each digit is 8. Let me see here. It should be X start plus 8, not 9, 8. Okay, so this is, my X range and my Y range is gonna be the same. Y start, here Y start plus 8. In other words, what I'm doing here is I need to locate this point, and then I'm gonna put 8 by 8, which is the image, the handwritten image there. And the rest gonna be what? Gonna be the margins. And then this gonna be what? This gonna be say X, since I already have the axis. So I just need to have the row times number image. Yeah. And then let me see. Give me a second. Uh then which number? Row plus column. It should be plus the column. So think about it. Suppose I know the row is this one. So what is index of the handwritten digits in X matrix? In other words, I'm asking you in X matrix, which row it is. Okay, I've already known the row number. Each row is a 40. So that what I'm gonna have, suppose now it's here. What should I have? It's gonna be the full of the first row plus the column number, right? But the full first row is what? The full first row is, let's say, how many rows totally, and then times each row, let's say is 40. So that, let's say, suppose here is 1, 2, 3, 4, 5, 6, 7. How can I get this 7? This 7 equal to the number of rows equal to 1. One row is behind me, times each row is 4 numbers, 1 times 4, plus the column is 3, 1, 2, 3. So that's the thing. Of course, because X starts from 0 and your column also starts from 0, so it doesn't matter. I mean, you name this one to be 0, you name this one to be 1, doesn't matter. So I should have this this function. And then let me see, give me a second. Sorry, here is I need to have a wait. Here. No, I need to have a reshape. I remember before when I write a code, when I prepared, this one's always wrong because I always forget this part. Because here it is X start to X start plus 8, Y start to Y start plus 8. This is actually at 2D dimensional, which is like one image, here, which is 8 by 8. And then I need to reshape it to be 8 by 8. In other words, what's going to happen is that, well, for each, this small cell is 12 by 12. And I'm gonna have, let me use a red color. I'm gonna fill it by 8 by 8. So this 8 by 8 is what? The real digits. I mean, the 8 by 8 pixels. And all others gonna become margin. So that's how I wanna construct my image plots. So it's gonna be something like this way. So let me try it. Probably gonna be some error because I remember when I prepared this slides here, it shows a lot of errors in this conversion function here. Image. And then I need to make it, I believe. Yeah, I need to make it a CMAP, a binary. Yeah, oops, sorry. In other words, I need to have this thing RGB to gray. So I need to have from let me see what is that SK image. SK image dot color image dot color import RGB to gray. So I'm gonna have CMAP equal to binary. And let me see here. No, this part here you may not need it, but later you will see one thing. And then I will have let's say PLT dot IO, which is the image of the training digits. Okay, where we are. Uh, Gray, oh, GREY. Really? As great GREY? Why in my mind is GRAY? Interesting. Okay. Let me see here. Uh-oh. See map. See, ah. Oh, great. It works. Because I worry that this part is gonna be wrong. This part is super easy to get wrong. Let me see what I yes, looks correct. Okay, so these are the digits here. So here we've plotted 40, probably 40 by 40, which is 40, so 1,600, while the total number is 1797. So these are the training digits. And we want to use SVM to train them, and then we want to what? And then we want to, make the prediction. So what we can do here is what? Is how the next part is that we need what? We need just see how can we do the SVM part, right? But first of all, I need to have the test data. So for the training part is actually extremely simple, but how can you actually test it? The test data is here. Where am I? The test data are here, so that I already generated. Then I'm gonna, let me see here. Okay, let me just continue it. Oops, sorry. So now what we can do is we want to train the data, train the SVM. So I'm gonna have model dot SVG. Here I just use the default kernel, which is RBF, and also default C, default gamma. Default C is equal to 1. Default gamma is 1 over number of features times variance of X. Okay, and now I can have model dot set X and Y, where this X and Y's are just right here. Be careful that X is not a tensor. Okay, X is a matrix. It is, it has 64 columns. Okay, now I can just, first of all, I can print the training accuracy, I believe. Let me see, did I? Oh, yeah, I did it. The training accuracy. Print the training training accuracy is model.score x and y. Okay, and then after we need to what? We need to plot those kind of training data, right? And then we can see here the path is right here, and the data are, I believe, all RGB. Yeah, all okay. So for example, you can just because that's the pixels 8 by 8, so that's why it looks very, very small. And that's the limitation of SVM. If you have many pixels, no, immediately using neural networks. I hope I have time to give a lecture. You can even build a neural network by yourself, which can greatly help you the meaning of neural networks simply, rather than simply using existing library. Because to be honest, the soul of machine learning is mathematics instead of coding, because coding is really just some basic thing. And then we have the path of this one already. So since the names are all the same, so I just want to kind of like to be lazy. Let's say to generate the path for the training for the test data, not training, test data. So I first of all already have path equal to this. Okay, now I'm gonna have a special path for each images, right? So I'm gonna have a create thing, and then I'm gonna use append to make it. So I'm gonna have image path equal to empty first, and then for each one, because my things are what? My things from 0 to 9. In other words, that's a range 10. So I'm gonna have for I in range of 10. What I'm gonna do is let me see. I'm gonna have the name is what? DGT. Okay, the name is, let me just copy and paste in case. Name equal to, let's say, DGT, but be careful here when the double slash, because if you have only one slash, it will make the error. Let me show you why. I can just, let me just, actually I don't have to. I can just do it like here. Since I have several cells, let me print path. See it? And then if I have, let's say, print path, let's say print name equal to, let's say, DGT, then print path plus name. Actually, yeah. Let me see. Because I remember I test, or during my test, it was the previous like Python system. If I write one slash line, it's gonna be wrong. But we can test it, it doesn't matter. Plus string I. So it will give you the DGT whatever number, and then plus you need to plus another number, which is .jpg, because all their format are JPG. And then finally, you can just have image path dot append name. So it will, have everything. This one, DGT1, DGT0, DGT1 plus blah blah until DGT, DGT, whatever the name, let's say 10. Okay, so if I write in this one, give me a second. Let me just test this part, just make sure everything's correct. And then if I print, let's say image path, here we go. I will name equal to, give me a second, give me a second. Here I should have path plus this. Where's the path? Give me a second. Yes, and then append this one, and then let me see. I need another path. Sorry about it. I need to have another thing, which is, let's say, for I in range of 10. Image path I equal to path plus image path I. Okay, here we go. Great. So now that's the thing. For example, the first one gonna be this name, the second one gonna be this name. So now I've already, got everything. I can just kind of paste all this in here. So that, okay, now I have all the training, the test data, the names, and then after I have the names, what I need to do is simple. I just need to, let's say, sub the result of prediction and the test data. data digits, let's say. Okay, so now I just need to create a figure. If PLT dot figure. And then I can have, let's say I equal to 1, meaning the first one. And then so I can say for let me see for image for let's say image path. For each path, I will create a what? Image path. Then I'm gonna have let me see. Here is I can directly have the image equal to PLT dot and read that image path. So first of all, read the image path, and the second thing is I need to print. However, be very, very careful here is that the images here, although it looks for us, it looks like kind of like gray. Let's say it looks like black and white, but the truth is that it's not really black and white. It actually includes many like different colors, because if you have a look at, let's say, let me see model equal to this image show image. If you have a look at the X, it actually includes kind of like 16 colors. Let me see. How can I? Let me see whether I can. Or another way is, let me see, I may directly just print X. Give me a second. Oops. Here you can see it has 16, it has 9, 1 something. But what we need is something black and white. And hence, what we want to have is to include this one images color RGB to gray. So we enforce it kind of like to be, the gray. And then another thing is that I can give me a second. I can make it to let me have a look at what I do here. Sorry, a bit forgot here. Okay. We have the grayscale image. So we enforce the image to be grayscaled. Here I use RINT, means round into integer, so that we enforce everything to be integer, because otherwise it will get, like the float 16 point. That means 16.0. I want everything to be integer. And then I'll use these conversions, because if we don't use this conversion, it will be the opposite. Let me first show you. Okay, let me have this one. Let me show something interesting here. Okay, so here I have this one. I have the images here, right? And then I have this one, grayscale image equal to mp dot int. So first of all, let's see. What if I just say RGB to gray? So I just want to push the RGB color to gray. So isn't it good? I just want to directly plot it. You will see something opposite equal to FID dot add subplot. Let me see 2 phi I x dot and show grayscale image. See equal to binary. Digit image is big grayscale image. Let me see. I need to reshape probably. Let me see. Yeah, reshape 164. Okay, so then I'm gonna have what? I'm gonna have I plus equal to 1. Where? 20, 28. Uh-oh. Okay, here. Are how come it's not defined? 48. I'll just define RGB. Also, let me see here. What is wrong again? It's not callable. Why? That's weird. I remember I put a reshape there. Okay, the reshape 160. Let me see how many things here. Wait, I have so many. Let me just I believe this is the last one. Let me rerun it. Sorry, it's too many. Just okay. Uh, yeah, didn't you see something interesting? That is the opposite. You see it? I want the number to be black while the background to be white. But so the reason because of here. But if I write in this way, it's going to be the opposite. The reason because the library here of RGB, I mean the function of RGB to gray. I don't know why they make it like this way, but they kind of like push it oppositely so that you have to manually convert it, which means 16 becomes 1, 1 becomes 16. So that's why what I wrote is here. I use this function, 16 minus this one to brutally kind of like reverse it, minus this one times 16. So in this case, it will be the opposite. Let's rerun it again and you will see. Okay, here we go, see it. So training accuracy is this one, 99%, which is pretty good. And then you can see indeed all the numbers are correct. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's how we can make it. Of course, you might say that, I mean, why make a number like this? So why don't I just rewrite it and you want to see? Well, what if you're cheating, right? Okay, no problem. I can just, let's say today is May the 9th. Let me just rewrite a 9. Let me just use the paint. I hope it's not too bad. Okay, so here we go. And then first of all, let me just reduce everything. And then let me just plot. Let me use a plot. Okay, now I need to write a 9. Let's say I write a 9 like this way. This looks like 7 actually. This, I don't know. We can try it. 16 digits. Let's say this one. Okay, now I just save it. Okay, digit 9. Let's see whether whether it's gonna be still the same thing. We can run it. I mean, you can play whatever number that you want. It's not a big deal. Okay, here we go. And you see it. This is the same. I'm not cheating. I can just show you that. I mean, I just want to show you they're the same number. You see, this is the number I just plotted, you see, if you make it small, So it's still 9, see it? It's actually pretty powerful, to be honest. So that's a very good result because you can see like how fast the training is. So that's the thing. Of course, I mean, if you want more complicated, more accuracy than neural networks. And yeah, so that's the thing. This is one of my favorite example in SVM. Okay, so I believe that's everything of. Oh, wait, we have one more. We have one more thing here. Okay, so it's already this time because I do want to start a little bit for class 3. So the code is here. Sorry about it, but I'm afraid I'm gonna kind of skip it. This code are basically the same as this code because it's both make moves the data here. So what you need to do, the only thing here is instead of for kernel for gamma, what you need to do is just for different classifier. So here what we do is that we've learned KNN, we've learned naive Bayes. This one because it's from the Gaussian, so all continuous features. So we're gonna use Gaussian naive Bayes, a logistic regression and a SVM here. So I do want to make a comparison for the KNN. I use a phi NN Gaussian. Gaussian just Gaussian. LGB to save my life. I use linear solver. For SVM, I just use everything default, which means RBF kernel C equal to 1 and gamma equal to 1 over n feature times x variance. Okay, so the codes are here. And again, we use those things, this notation. Feel free, here I said what? I said this equivalent to here. Okay, so in the last example, I actually already used that technique, but the same thing. The thing is you can write a 4 or you save your life, you just write one line in the list. And then we have this, and then we split the data set to be the training and the test data set. And then we have the names, which are classifiers. sorry, names of the classifiers, and classifiers are the real classifiers here. And then you can, just subplot the things and then use a for loop. The for loop here, be careful that where's my training part? Let me see my, I cannot find my, here, let me see model. Okay, here we go. So this is the part that I can actually be lazy. Okay, Zoom gave me a something here. Let me make it very thin. Okay. So the part is this one. So this one you can see that because I've already defined the classifier, and so I can there say model equal to classifier where my classifiers are this. So these are just the classifiers that you import in the very beginning, so that you can directly use a for loop. So the name is in the names, classifier is in classifiers, and then respectively, okay. And then you have the model equal to classifier, model.fit equal to this moon data, train data, and the moon X train data, moon Y train data, and then make the mesh grid. And all other things are exactly the same thing as we just mentioned. Oh, sorry. As we mentioned before, and then we added the text. This is almost everything the same as we mentioned here. Add a test here. Don't make the mistakes in how you add a test about alignments. Okay, so here we can see the results. So original data here. Wait, here I actually tested two groups of data. One is called the moon. The other is called sorry, what's called circles. So moon is this one. Circles is this one. So here I use those kind of data on purpose to set up a difficulty. You know what I mean? So that you're gonna see why kernels are important. Without kernels like LGR, this result is really, not good for LGR. And you can see it's the accuracy is only like this way. By comparison, if we use the SVM with RBF kernel, look at the results. And the one thing really may surprise you is the KNN. KNN is extremely fast, and you can see the result. Here, well, here I already this it's more likely an overfitting. The same thing. So that maybe I made too little noise. I should have more noises. Okay. Oh yes, because the circle, the noise level is only 0.1. You are highly recommended, after the class to have a look at this and write the codes by yourself because I just want to save some time. You can test different noise level so that you can try to make the training result a bit worse instead of make it to be one, so that you may doubt, hey, is there something like overfitting? So that's the things. So this is a comparison. Indeed, when your number of features not that high and your number of data is not that many, a number of data n is not that many, SVM would absolutely be your first choice. However, when you have many classes or when your data have many very high number of features and tons of, let's say, billions of data, then the training of SVM could be slow. Why? Because due to the model itself. Think about it. In the models, we have this. Let's say the soft margin even for the soft margin for each data I have one constraint. So if you have 1 billion data, you will have 1 billion constraints. That's the reason why SVM for large data set, no matter the number of features has a lot or the number of observed or training data has a lot or the number of classes have a lot, SVM will have the problem. Then that's why people, now there's always everything's neural networks. So that's the thing. Okay, that's everything about the SVM and also about the whole classification. The next thing we're gonna introduce something which is unsupervised learning. So from the linear regression till classifications, they're all supervised learning. Again, let's have a review. What does unsupervised or supervised learning mean? So first of all, for supervised learning, we learn with a teacher, which means we have a given label. For example, in regression, we do observe y equal to, let's say, wx or beta x, and then in a classification, we do have a label, which is, let's say, moon and what's the name? Circle the data sets. I will have the label, which is class 1 or class 2. Or the thing we just mentioned, which is handwritten digits, we have 10 labels, which is from like digit 0 to digit 9. They are all labels. I'm gonna tell you, for example, suppose I write a number, say I write this, suppose this is training data, okay? I'm gonna tell you, hey, this is 9, this is 9. That's what I'm gonna tell you. Okay, now for unsupervised data, I will no longer observe this Y. I just give you, different data. You need to find the patterns by yourself to make a self-study. So for example, suppose I just give you this, I just for example give you this. I can even write a 2 here. I mean, it doesn't matter. I just 0, 2. Okay, then it's your responsibility to find the patterns by yourself. Say, for example, you can suppose you're very smart, you observe 3 different patterns, you're gonna have 3 different categories. Say these zeros are one category, ones are another category, twos are another category. I'm not gonna give you the label, hey, this is all these zeros are in one class, these ones. No, I don't give you this information. So this unsupervised data, unsupervised learning, clearly in general, unsupervised learning is more difficult than supervised learning. Okay, and then here's another thing. Say here for classification, which is a supervised learning, what I'm gonna give you is, okay, I give you 3 groups of the data, and I tell you the label. Okay, this is rather class 1, this is class 2, this is class 3, this is class 2. But in the clustering problem, which is an unsupervised learning problem, I'm just give you this data. And you can see all the colors are dark color. Not like here, I tell you 3 different colors indicating 3 groups. Here, all of them are the same. I just want to ask you, hey, do some, in general, data mining, find something. So what you should find here is tell me, hey, suppose, let's say I want a clustering, I want to make it, for example, to be 3 clusters. And then the problem is, how can you do it? Okay, so first of all, let's define the problem of clustering. Clustering is to group data objects to be clusters such that objects in the same cluster are more similar, or let's say more closely related to each other than to those in other clusters. So for example, points in this cluster should be similar or closer to points in this cluster. I mean, intuitively or visually, towards a picture, everybody knows how to do it. It's so simple. But mathematically, if I just cover your eyes, how do you do it? It's actually not a really simple, problem. So there are actually many clustering methods, and here are some very, popular methods. And today we're going to introduce one of the most famous one, which is the k-means clustering. That's close to the KNN. The K is also a hyperparameter. But the difference is that in the k-means clustering, it's a clustering problem in which I don't give you the labels. In classification, I do give you in KNN, it's a classification problem. I do give you the labels. Okay, now let's see how to do it. So the idea is given 2 data here, because here I defined more closely related. So I have a term close. What does close or what does similar mean? You need to define a similarity function, or here we can define a dissimilarity function. I mean, not a big deal because one maximum problem, one minimum problem. Okay, so for the dissimilarity, we can simply use the distance. Here we have different measures. Of course, the most common is the L2 measure, which is, the Euclidean distance. So this M means for a measure function for 2 data, xi and xj. I want to use L2 norm to, define the dissimilarity. Of course, the bigger distance is, that means they are more, let's say the smaller distances, they are more similar. The bigger distances, they are more unsimilar. I hope there's no unsimilar. So that's the thing. And of course, you can sometimes consider weight. So with this weight, meaning that some different features are, the importance could be very different. So that's the thing. Of course, we can use L1 norm or L0 norm. Of course, if you want, you can still put, a WK weight parameter here. Okay. And another very, very important measure is the correlation measure. So it's gonna calculate the correlation between X and Y. This is why do we use what in probability-based things. Let's say in this kind of algorithmic trading, I observe two groups of data. Let's say the price vector data of, let's say, stock of Apple, and another, let's say, price trend data of the stock of Microsoft. I want to see, hey, how correlated the stocks of Apple are with stocks of Microsoft. So this is a correlation, and based on the tangent data, let's say the cosine of the theta, between these two data, I can do many interesting things, like too many strategies. Let's say one of the most important, one of the most thing is like a long short strategy, which is I'm gonna buy one and a short sell another one. Anyway, if we have some time, I want to show something interesting, about financial things on Friday class, next Friday class, so Thursday class, sorry, if we have time. Okay, and then here's correlation, and we have a very familiar, we have a very important conclusion of the mathematical formulation for a general classification problem, which is here. Uh, I do want to mention this ones because otherwise there could be a problem. So, okay, so here's the integer linear formulations for clustering analysis. So this is the general formulation. Then people are gonna immediately ask, say, hey, since you are these two are equivalent, just three indices or two indexes, the same thing. So since you've already have everything, looks pretty good. I mean, why do I need to have different clustering methods, clustering problems? The reasons because these are integer programming formulations. If my training data are large, it's impossible, even not too large, that's even thousands of the training data in many cases, it's not easy to solve it. Not to mention billions of the training data. I mean, till the end of our lives, we cannot see the solution. That's why we cannot, just define one general clustering problem and represent all. No, that's why we have so many different things. Okay, so the k-means clustering means k-means. The k-means clustering means I want to assign the n data into k clusters. So the summation of this similarity measure of all the data to the centroid of their corresponding clusters is minimized. So basically, let me give me a second. Let me use this example. So basically, it's like this way. Suppose I tell you, okay, the number of clusters is 3. So I'm gonna have, for each cluster, I can get a centroid. Centroid means the center, simply just the average of all the data. So I can have, okay, let me use a shape. Let's say I have a star here, for example. Oh, why the plot is so ugly? Sorry about it. Let me redo it. I can have a circle, for example, here, and then, for example, I can have a circle here, and I can have, for example, a circle here. So these circles mean centroid, okay? So the meaning is that, well, suppose I have this is one cluster, and this is another cluster, and then this is a third cluster here. Suppose I have all of these, then I'm going to calculate the distance of, for each cluster, all the points, the distance from the point to the centroid, and then sum all of this, all the points here. I want to minimize the final thing. So that's the meaning of the k-means clustering. Then how can we make it? How can we have an algorithm such that, this the whole thing gonna be minimized? So here, the notations are C's means the cluster. Ci means which cluster data xi belongs to. And then this mu is nothing, just summation of all of them and divided by NL. And NL means the total indicates the number of data in class L. So this means the centroid. Okay, now what I'm gonna have the k-means clustering is to get the minimization of xi minus mu L. So this xi minus mu L means that for the mu L, which one? Give me a second. Okay, here, the L is here. L from 1 to k. So we're gonna consider what? All the k classes, but The second sigma inside the sigma shows that I'm gonna only consider it if your L is of class, if your L is the cluster of my data I. In other words, you can actually somewhat make it, to be, we only consider the xi minus its. It means the cluster which xi belongs to, its centroid. And then for all the data, you're gonna calculate the data minus its own centroid, the distance, and then summation all this I data. So that's the thing. I want to minimize this thing. And then another question is how can we determine the hyperparameter k? Because as we mentioned, the k is, is a given. So we can use this elbow method basically, which is as long as I see something goes down like here, this point, then I'm gonna take this one to be the k equal to 3. So here are some definitions here. If you're interested, you can read it. This is like it's kind of like an elbow. That's why it's called elbow method. Okay, due to the time limitation, I'm gonna stop my class here. And in the next class, we're gonna have a look at how can we do the k-means clustering and the algorithm and how to make it in Python. That's everything about today's class. Thank you.